Welcome to Hyperstition number 10, Orchestrated Objective Reduction and Brain Organoids. The subject of consciousness is often one that's treated right alongside intelligence. And we often think that consciousness and intelligence are perhaps the same thing, or perhaps two sides of the same thing. But I think there's reasons to think they're wholly distinct and different. For example, an ant colony can show and emerge in kind of intelligent behavior among all of its interacting agents, but there's no singular conscious entity we would assign as the inhabitant of that ant colony. Clearly, this is an emergent property. And these days, we approach the subject of intelligence primarily from the perspective of a computation, is that this is reducible to a set of algorithms or an algorithmic approach, and that because computation is universal, because such a thing as a Turing computer can run any kind of algorithm or calculate any function that can be solved algorithmically, and that perhaps next token predictors are universal function approximators, or other kinds of ML models may have this universal function approximator perspective, then anything that's computable can be rendered by an AI agent. And that if consciousness is the same thing as intelligence, well, then we can make conscious computers. But there's another perspective on this, and I think it goes a bit deeper. There are things that are not computable. There are physical processes that are not computable according to this conventional perspective of the Church-Turing thesis and lambda calculus. These are non-Turing complete computers. And before someone says, oh, this sounds made up or controversial. No, it's not. I mean, Alan Turing himself wrote about non-Turing computers. He called them oracle machines, prophets. And a non-Turing computer is something that can basically solve the halting problem, or it can get around this decidability issue. And it gets around that by exploring many possible threads of computation at once in parallel. Now, are there any physical computing methods that we have today that kind of sound like that? Oh, yes, there is. There's quantum computing. Quantum computing explores many possible solutions at once to the same problem, and so it can solve problems that are otherwise perhaps undecidable in a conventional Turing computer. And so this brings us this question of consciousness, is that consciousness may involve physical processes that are not conventionally computable. It may involve processes that look more like a non-Turing computer. And those processes are inherently quantum mechanical. They exist in a superposition of multiple states at once. Now, orchestrated objective reduction is really the only theory of consciousness I know that has actually put forward a testable framework to understand whether these are quantum mechanical processes occurring in the brain. And they primarily have the view that it is microtubules in the cytoskeleton that is engaged in these quantum mechanical processes. And it's not just that information processing might go on in the cytoskeleton, but there's actually a component to this that's proposed by Roger Penrose, and the theory has been developed by Roger Penrose and Stuart Hameroff, that there is a gravitational influence or gravitational coupling between structures in the brain and quantum mechanical processes. And so this is testable in a physical laboratory. And so this is probably one of the more interesting topics you can get into in the world today. And someone that I respect greatly that's working on this is James Tagg, and he is our guest today. So welcome, James. And so James, yeah, hello. So you're not just working on this topic of, I think, like experimental physics and investigating this orchestrated objective reduction issue, but you also happen to be the inventor of the capacitive touchscreen, or you're one of the primary inventors of this thing that is now in billions of devices. So I'm curious kind of, where did you start? How did you first get into this stuff? I mean, how did you go from, I think, consumer electronics to now, like, entangled photon experiments?
Well, it just takes a long time to get from A to B, right? Yeah, so we were building a damp meter originally for, in England, England's a damp place, right? So what happens is that you build a house out of bricks, and then the water seeps up the wall. It goes through a damp-proof membrane, which then kind of breaks down. And so what used to happen is builders would come to your house and they go, oh, it looks like you have some damp. And they would get this machine out that has 2 pins. They'd stick it into your wall all over your house. And that was a moneymaker, because if they found that there was damp, because the resistance, the water in the wall conducted the electricity, the resistance was low, they would then fix your damp proof. If they didn't find there was any damp, they'd stabbed your wall with these prongs, wrecked your wall, and they had to replaster and repaint it anyway. So it was a fantastic moneymaker. So we were making a capacitive damp machine, right, which would basically see whether there was water in the wall. And that really never went anywhere. But a sort of an inventor turned up with a talking book toy, where you touch words on the page, and Winnie the Pooh goes, hello, can you spell this word? And you would touch the word. And of course, it didn't work because kids' books are board books, right? They're made out of cardboard. So you press one of the buttons, and all the buttons fire. So he was in tears because his invention wasn't working. And we stuck our damp meter behind it. He put his finger on and said, look, you can detect the finger through a board book. And so we made this child's toy that detected touches on the book. And then we got a piece of glass from a local kind of glass glazing company, and we scratched the coating off it. The coatings on glass are indium tin oxide, which is conductive. So we scratched them all off with a diamond scribe and made the first transparent capacitive touchscreen.
Okay. So you went from basically in-home mold testing to children's books to capacitive touchscreen.
Correct. That's the origin story for the capacitive touchscreen.
No way. That's wild. And I mean that's like the most consumer facing like electronics thing, there is today. Like one of them, right? Like alongside, I don't know, batteries or something. And then now today you are working on testing theories of consciousness, and not just, academically, but also looking at developing computing brain organoids as well as part of this experimental investigation. So I'm curious, like maybe you can help us understand, like what is Valis? What are you guys doing? What are you guys working on? Kind of what's going on?
Well, I'm an engineer, right? So although the theory stuff is really fascinating, there's lots and lots of well-paid theoretical physicists in the world who can do lots of theoretical physics. So I prefer to do stuff where you think of some sort of an experiment theoretically, and then you can actually build it. So the one behind me was our first physical experiment that we built, and that is an objective reduction testing machine to see whether, we'll explain this in a moment, but to see whether the quantum wave function collapses or not. So,
but not just, whether it collapses or not, but I think whether there's a gravitationally mediated interaction of some kind.
That's right. Yes. So all wave functions, well, we don't know, right? I could say all wave functions collapse, but the majority of physics still think Everett is possibly correct. So Everett was this physicist who said, whenever a quantum thing happens in our universe, and there's a guy that actually sells a watch that is a quantum watch that will say yes or no. So you can say, should I date this girl? Yes or no. And a quantum number comes up on the screen and tells him whether to do it or not do it. And because that's a quantum event, the universe then splits in two. So depending on whether he has the watch that said yes or what the one he has no, right? There's another universe in which the watch said yes, and he did date the girl. So basically, you have this idea that every single time anything quantum happens, the universe splits into two, and we get both universes happen. Now, of course, this is ridiculously inefficient because every photon going through every glass of water. Do I have a glass of water? No. Every glass of water, every time a photon hits, an air glass barrier, some of them are reflected and some of them are transmitted. That's a quantum event. The universe splits for billions and billions of times a second for every glass of water on the planet. It just generates this enormous soup. So, but that still is the sort of default assumption of physicists that we live in a sort of a multiverse.
Yeah, I think that's David Deutsch's conclusion. I think he's a multiverse proponent.
He is a smart guy and he evolves his thinking. So certainly the last time I looked, I think you're right, but I've seen quite a lot of things from him over time where he's exploring these things. So he's not set in stone. There's some people obviously who are set in stone, like complete multiverse people. And then you have sort of reduction people that say that no, it drops out. We don't get an infinity of universes, we just get one. Certainly we get one after a period of time. Now, if we never got multiverses at all, then quantum computers wouldn't work, because quantum computers use this sort of parallelism to do computation. But generally speaking, they collapse quite quickly. So, but some things take forever to collapse. So we can do collapse experiments on light coming from quasars on the other side of the galaxy and show that they didn't collapse for 14 billion years. We can do in the lab, IBM regularly keeps their stuff going for 100 milliseconds. And you've got a few people who can keep quantum states going for a few hours. So they do hang around, but the Roger Penrose, DOC, various different people think that it collapses and that we end up, with just one reality.
Well, let's kind of get into this then. I mean, I think this is a really interesting topic. So, how does this objective reduction differ from sort of conventional interpretations of quantum mechanics, or is it the same as this Copenhagen interpretation where?
I've lost you, Andrew. Will? Well, I have silence from Andrew, but I know the question he was going to ask, so I'll start answering it just in case I'm still online. So it's basically this difference between the Copenhagen interpretation and collapse. So the Copenhagen interpretation is a bit odd in that it just says when you observe, it just says what happens. It says when you make an observation of something that is in two places at once, the quantum superposition problem, you find it only in one or the other with a probability 50-50 if it's gone through a 50-50 beam splitter. And to some extent, it's like a shut up and calculate, right? Which is, this is what happens. This is the maths. It does this. When you look at it, you find it in one place. When you don't look at it, you can prove that it was in two places at once, right? And you can do that on an IBM computer. I do it quite regularly. You just type into Claude, please put this IBM computer into superposition and then prove that it is in superposition, and it'll just write you a program and do it, and animate it for you if you want. It's fantastic. So you definitely know that you can put things into superposition, and when you look at them, you never find them in two places at the same time. You find them in one or the other. So Copenhagen, to some extent, just says that's what happens. Don't try and think about why or how. Just live with it, that we just don't really understand how it works, but it does work, and the maths is perfect, and it's accurate to 14 decimal places, and we build machines and that work completely reliably. So Roger Penrose says, no, that's not physics. There should be a process, a physical law or something that causes it to get from this quantum state to the gravitation, to the collapsed state. And he's done some maths, and DOC from Oxford also did some maths. And they basically said that if you put something into superposition, from a quantum mechanics point of view, you're fine, right? You can have two things in two different places, and all the Everett maths works, and they just sit there in these two different states, and then when you make the observation, you find them in one or the other. And I should say, for the hardened physicists out there, when I say in two places at the same time, lots of people would be very uncomfortable with that. They would just say, there is a joint state. There's no two places. There's no same time. It's just, we don't know where they are, and then we do know where they are. So it's a sort of a problem of knowledge. So the Copenhagen interpretation is basically, it says once you know what's going on, once you attempt to know and you do know, you'll find them in one place or another. When you don't know, they're in this joint state, right? Or this superposed state. Penrose says, no, there's got to be a reason why it goes from one to the other. And he says, okay, quantum mechanics is sort of fine, but general relativity is not fine. You can't have two masses in two places in space-time because space-time is a surface, right? And so, if it's bent this way because there's a mass here pulling it in this direction, we normally put masses down here conventionally because we sit on the planet Earth, it doesn't really matter. If you have a mass that could be here or could be here, you have two space-times. Well, this has got to either be this one or this one. You can't put space-time into superposition. It's one thing.
This raises a question, which I've never actually thought about. So you suppose you have two particles going, one of either way. You don't know which, so it's sort of a superposition of two possible positions. And then but the particle represents some amount of mass energy, and normally that deforms space-time. And so we don't see two deformations that are each half as big as one or the other, or something, like it's not split up.
No, we don't. Well, it's very difficult to see them, right? Because the gravitational effect of a tiny particle is really unmeasurable. But it can't be the case because that's not the way that Einstein's equations work. And you can then go through some maths and show that there's a paradox, which means that the maths must be wrong. So you've got to fix the maths and fix the idea, how this all works. The question then is, can you think of a clever experiment to see that two things are actually in two places at the same time gravitationally? Is there a trick? Because you certainly can't do that with some sort of mass detector, because the masses are so tiny. So you've got to find a trick. Now, some people are trying to do some direct mass measurement techniques, but then you've got to have enough mass in superposition, and that means putting very massive things into superposition, and that's tricky. So it's, so it's go on.
Yeah. I was gonna say. I mean, I know you've been approaching this experimentally. I'm curious, how have you been approaching this kind of question experimentally?
Well, we put heavy things in superposition, so that's what we do. But we do it in a way that most physicists would think is ridiculous.
Okay.
So we make a measurement, right? We get a photon and we put it into a single photon detector, like a Geiger counter type thing, and it will give us a click saying there's a photon, right? Now, the question is, was a detection actually made when that happened? So single photon detectors have got smaller and smaller. I've got a whole bunch on my wall here, but they've got smaller and smaller and less mass. So now a single photon detector is a 4-atom thick film deposited on a chip. And when a single photon hits it, it knocks an electron out. You have 200 volts across the chip. And so as soon as an electron gets free, it's going to whiz to one end or the other. And as it whizzes down the surface of the chip, it knocks other electrons off. And there's a cascade. So you basically have a single photon comes in and you get a belt of energy coming out. Now, I accidentally touched my experiment once while it was on. And I can tell you it's about, you'll think about it for the rest of the day. It's not life-threatening. But it's certainly, it's a lot.
Yeah.
Let's see. Yeah. So this is so we basically take a photon and we split it in two, right? We put it through a half-silvered mirror. Then we detect it from two different single photon detectors, and then we move two mirrors or two slit. So imagine, most people understand the Young's double slit experiment reasonably well, right? So you take some light, you put it through 2 slits, and on the backside you get an interference pattern. You get light and dark fringes, and you can pay $12 on Amazon and get one of these and shine a light through it and do it in a darkened room for your kids. And it's the cheapest way you can play with quantum mechanics efficiently.
Okay.
Yeah. So we said, well, what happens if you close both the slits? Well, if you close both the slits, you get nothing. What happens if you close one of the slits? Well, if you close one of the slits, you get single slit diffraction, which is still a pattern, but it's a very different pattern. So what happens if the single photons dump some current into 2 solenoids and they suddenly open the mirrors, the shutters, right? If gravitational collapse takes some time, what will happen is both shutters will open in superposition, and then they'll go, oh, we can't be in superposition because we've exceeded some gravitational limit. We better not do that, and one of them will close, and you'll see the eventual result that you always see in an experiment, which is only one of the shutters moved. But during the time when it was in superposition, you potentially should see the interference pattern from them both being open. So you should see double slit interference and then single slit interference. And the question is, how long does it take a certain amount of mass to collapse space-time?
Right. There's this hidden formula in here that I've seen, which is like the time something can be in superposition is like 1 over its mass or something, right? Like it's
okay. I mean,
there's
an equation.
Yeah, there's like this relaxation or whatever this time constant.
Yeah, there's an equation, but it's nicer to understand why there's an equation.
Yeah.
Right?
Yeah.
So the idea is space-time can be in superposition while we can't prove it's in superposition. As soon as the Heisenberg uncertainty principle number is exceeded and we're certain that you have 2 spacetimes, you can only have one. But while we're underneath the Heisenberg uncertainty principle, right, we can't be certain that we have 2 spacetimes. So effectively, we're in an undecided state. And does
this kind of imply that the differences between 2 spacetime configurations are themselves quantized, that there are discrete configurations it can take on?
I mean, the answer's got to be yes, right? Which is that gravity is currently a classical theory. So there is no quantization of gravity.
Yeah,
it's just a smooth theory. All the equations are smooth, whereas quantum mechanics is a quantized theory. Mm-hmm. So we need to fix the gravity equations so that they're quantized. Now, Penrose is fairly firm of the opinion that gravity is not the biggest problem here, that quantum mechanics is the one that's basically at fault, and that gravity is sort of right, although there's probably some quantization of gravity required, but it's not that you've got to gravitize, quantum, make a quantum gravity theory. The fundamental problem is that quantum mechanics is wrong, and so you've got to fix quantum mechanics. Well, so in the process, it's a sort of, it's a concept really, because you're going to fix both and bring them together and unify them.
Back on that a little bit, because I think, earlier this week I had a friend on here talking about superluminal causation in quantum mechanics. And the thing with this entanglement experiment to start with is that it supposes that there is that superluminal causation is possible, and that we know that this is not the result of some deterministic hidden variable theory, because of Bell's inequality and Bell's correlations, which are measured with experimental systems. So it's like, we already know that, this is my perspective, but we already know that some of the premises of GR in terms of causal light cones and causal light cone interactions is wrong. Whereas we have more measurement basis for accepting this entanglement principle experimentally. So it's funny that we're trying to save GR and its assumptions here and then modify quantum mechanics when I'm not sure if that's like the experimentally validated approach.
Well, we do have one thing in gravity that does break causation, and then that's these Einstein-Rosen bridges, where you can punch through from one piece of space-time. This is how you explain, Star Trek warp drive. Here's space, it's flat. We bend it round like this, and then we punch through from one side of the piece of paper to the other. I get a piece of paper in the moment, but that maths, the Einstein-Rosen bridge maths, does work. That would allow you to go through a wormhole and come out the other side of the wormhole, although you'd be scrambled in the process. There's a causation issue. Now, people can fix that by saying that the thing is, any information that goes into the wormhole gets so scrambled that what comes out is energy without any information, and therefore there's no problem, there's no causation, because you can't send a single signal back in time, and therefore you can't say kill your grandfather and someone shoots your grandfather for you. So it sort of solves that problem. But you do have at least one causal problem in gravity. Now, I mean, the OrcoR theory, there's a chap at Google who runs their quantum AI division, and he says it's got to be wrong. And he says it's got to be wrong because if OrcoR is correct, you can signal faster than the speed of light. And that is true, because you can, in my experiment here that I've got up, you can basically toggle the thing on and off, and then you can see whether the interference pattern switches on and off. So just move my interference pattern to Alpha Centauri, and now I can switch it on and off, and that will transfer signals faster than the speed of light. So Hartman-Evans says, objective reduction OrcoR's got to be wrong, because if it was right, you could go faster than the speed of light, and we know you can't go faster than the speed of light, so it must be wrong. But of course, there's nothing in Einstein's equations that says you can't go faster than the speed of light. You can't approach the speed of light from below because it requires infinite energy, but you can have something that's going faster than the speed of light. So nothing against that. So one of your fellow podcasters, Sabine Hossenfelder, has done like 3 videos now on this. You can go faster than the speed of light. It's not forbidden.
That's interesting, because I think that's often people always say within Einstein GR, you can't go faster than the speed of light. But this is things that maybe are already moving faster than the speed of light. This is like a tachyon, and from our frame of reference, it's going backwards in time. Like we see it traveling into the past, because is that, or am I kind of conflating things?
No, that's fine. I mean, the problem is we haven't found them, and they're a theoretical particle, and sort of hardened physicists are just going to go, well, that's nonsense. But they won't say it's nonsense that the equations forbid, faster than light things happening. They're completely consistent with the equations. It's just that we don't see them, right? Or do we, right? If you build an OrcoR experiment and you see that it collapses and it's built in a particular way, then that in principle is signaling faster than the speed of light. So maybe you do see it. Maybe something else protects us from causal problems, so that we don't live in a universe that makes no sense.
Right. Or I think the Stephen Wolfram perspective on this would be that our construction as observers is perhaps something that only perceives the forward arrow of time. And so we are forwards in time observers, right? And that maybe differently constructed observers, certainly something that's, maybe observer, what does that mean? Something that's the size of a quantum mechanical system perhaps is receiving information from both the past and the future.
Yeah, I mean, if you can go faster than the speed of light, then you can send signals back in time and so on. What that destroys is relativity. It doesn't destroy causation. You still have one direction in space-time which is always going forward with respect to all other frames of reference, and that is sort of like true time, and everything else is false time. So it does mean that we lose this kind of elegant relativity thing where everything's relative to each other and it all kind of works, but you do end up with a true time.
How does things, if you have fast and light information signaling such that things could receive information from their future, how would that not break causation? Because I think we often think of causation as one thing happens before the other, and whatever, adult ducks lay eggs, turn into baby ducks, right?
Oh, well, quantum mechanics comes and saves you. If you're in kind of classical thinking, if I send a message back to a friend of yours and say, if I send a message back in time and say, please, kill my father or my grandfather, and that's acted on, I disappear, and it causes a paradox in space-time, and we're going to sort of assume that we don't get paradoxes. So something that generates a paradox can't happen.
Mm-hmm.
But of course, I can't send a message back in time with perfect fidelity. So some of the messages get scrambled, some of them get through, some universes I get destroyed, some I don't get destroyed. So we end up with this sort of soup of probabilities, and some universes it happens and some don't, and then Penrose basically prunes them out because of gravity, and we end up with one space-time that goes forward along a preferred timeline, and that's true time. That's the true future of the universe. But there's lots of mess in the way that you get there. So it's it's a different way of thinking about things in terms of the way that space-time would work, but it's not completely outside of physics, but it's definitely something you'd have a pretty aggressive argument with many physics professors out there. They would just go, this is ridiculous. No, relatively, we can assume relativity is correct. We can assume causation is correct. All we need to do is to tidy up quantization of gravity and solve this relatively simple collapse of the wave function. And some people would argue that they've already solved it and it's done. It's just decoherence, and it's just loss of information, and we're done. There's nothing to explain. Now, of course, it's very disappointing because Star Trek and fast light travel and, aliens, and, we're never going to find any aliens because they can't go faster than the speed of light or signal faster than the speed of light. And although the universe is enormous, they're spread out with such a low percentage that we're just never going to see one before we stupidly blow ourselves up with our own nuclear weapons. That's one sort of way of thinking about the world we live in. And the other one is that, some of this slightly wacky stuff does happen, but with very low probability, and we could go faster than the speed of light. We could signal, across the universe and things like that. But it's a different set of physics, and Star Trek and the sort of wonderful science fiction things we have out there don't go anywhere deep enough into what happens if causation is really that flexible. That would be very worrying. So because if causation is very flexible, we'd a lot of weird stuff would or should happen, and we don't see weird stuff. Let's face it. Well, we see some weird stuff, but we don't see weird causal stuff.
Most of us don't have, and I think this is why specifically this theory, that this interpretation of quantum mechanics and this kind of the theoretical physics framework, I think leads to this really much more interesting question of experience, right? Because I think most, everyone, time goes forward, right? But then there are some people who have these crazy experiences of premonition or things like that come up at the level of experience. And I think the question, you and I have talked about this in the past, but it's sort of like, do things actually occur according to the random chance with which we think they should? Or do we actually, and this is kind of a weird question, but it's like, do very low probability things actually occur more often than we would expect? And this is kind of like, I would say, like, because if we have this reverse causation possibility, then there are some things that are like creating themselves or something. There are some maybe there are in the sense of like there's one true timeline along which everything else is evolving, and these kind of paradoxical universes are perhaps like destructively interfered out of how things evolve. So we kind of have this like some coherent timeline. There may be then sort of these strange attractor basins in the space of possible timelines, like very high likely outcomes that are somehow having this retrocausal self-influence. I mean, maybe this is kind of too out there, but I don't know if you.
Well, I go to quite a lot of conferences where not the majority, but probably a third of the people at the conferences think that this stuff happens all the time, and will regale you with their experience, their most recent experience of it. And so, I mean, I'm skeptical but open-minded, right? So I don't want to say this stuff never happens. We don't see very much evidence of it. So if it does happen, it's very rare. Unfortunately, most of the experiments that are done, the sort of sci experiments about remote viewing and backwards in time information and so on, are largely unrepeatable.
Right.
And I don't think it's the fact that the experiments are unrepeatable and it's a very difficult topic. I think it's that when you meet someone who's done one of these experiments and believes in it, they tell you that as a matter of fact it's true and that everyone should believe it and it's obviously correct, and what you're mad. I go, hang on. That there are some experiments that show some slightly weird stuff. The problem is when you try and duplicate them, it's very hard to duplicate them. But over many, many, many years, there have been experiments that show that people can predict what's on a bit of paper that's hidden from them very, very slightly more often than chance. And these sorts of things like that. So could there be something where unlikely events are slightly more likely than they should be? Yes, there could be. Have there been some experiments on it? Yes, there have been some experiments about it, but most scientists, physicists would say that those experiments are deeply flawed or just fraudulent or whatever, which is, I think, is unfair on the people who are attempting to do those experiments in a genuine way. But there were plenty of people who've done them in a sloppy way or even fraudulently, and so that's the problem. Yeah. It all dates back to when science was much younger, and you had lots of people saying clairvoyance worked, and you could talk to people had died, and then tricking people out of money through the process of doing that.
Right.
Well,
so an interesting historical anecdote on this topic, and I mean, I opened with this idea of computationability and Turing computers, and the search for intelligence and the conflation of intelligence and consciousness. One of Turing's things he said about the Turing test and the test for these things is, he wrote this, was like the undeniable presence of psi influences and the existence of telepathy. And
well, he was earlier, right? Earlier in physics, we didn't have this complete assumption that psi phenomena were woo-woo bunk. And many physicists, Schrödinger and Turing, discussed them, kind of believed them, and so on. But then I think there were so many bad experiments, or maybe fraudulent experiments, that the scientific community just flipped over to, this is all rubbish and nonsense. We're not going to spend any time on it. But Turing said, when you're doing a Turing test, you need to make sure that there are no psychic phenomena going on. Otherwise, you can tell it's not a machine because you don't get a psychic vibe from it. Or vice
That's
versa.
Exactly right. I love that. Well, I'd say, okay, I mean, we can distinguish two things here. One, like, I mean, this is your line, I'm going to steal it, but like cell phones have telepathy, right? Like this non like visual field or whatever information via electromagnetic waves. certainly can be reaching our body, certainly could be coming up the level of intuition and, this kind of stuff. I mean, I
Yes,
can't
it could
rule
be.
that.
I think my standard line is many fish, like a third of the things in the ocean, have what we would describe as telepathy. If we did it, if I was able to sit in a room and communicate to you without opening my mouth, right? Or nodding my head or whatever, we would call that telepathy, right? Many fish use electromagnetic signaling to signal, right? And when we came out the ocean, we just didn't work out a way of doing that on land. There seems to be no evidence that we're able to do that. But the idea that's ridiculous, not ridiculous. Lots of fish do it. It's just there doesn't appear to be any evidence that sadly, that we can do it. But
Well, this is, I mean, another thing with this topic that's tough is because, and I think this is rife throughout physics and our discussion on like this, Einstein must be right. And it's like the epistemological boundary conditions you're willing to accept, right? So if you start from the premise that this is impossible, anytime someone comes up with evidence of it in some way, you're like, well, this has to be wrong for all these reasons. And so there's this like documentary came out recently, telepathy tapes, and people can like take it apart for various reasons and whatever. But I think it's tough to say that there's no evidence for these things. It's just that the evidence is not up to the standards of scientific scrutiny that we would use to upend so much evidence for things being more conventional, right? And so it's the standards of evidence, but it's also, there's something weird here where it's like this electromagnetic signaling is one thing. That's perfectly classical, forwards in time. I send you a cell phone call, whatever, it gets there like a microsecond later. But the backwards in time signaling is like a different kind of telepathy. This is a different kind of conscious phenomenon altogether. And I guess where do we, okay, so let's kind of, from this orchestrated objective, or I guess this is actually just the objective reduction part, is this theory of physics, whereas this gravitationally mediated collapse of superposition, and that this gets us to a certain kind of theoretical understanding. For you, where do we then take that into this realm of consciousness and experience and like organoids and this kind of thing? Because it's like these are kind of very different realms, but I know you're working on both. So
yeah, I mean we've got into sort of heavy quantum physics for a while. So I mean I started thinking about this question of whether computers were machines. Now, of course, this was quite a bit before we had very, very good AI. Now we have very, very good AI. It's quite scary how close they are to thinking. But the question is, do we do something that is definitely different to a machine? And there we have to kind of look at Turing and Gödel and so on and say, well, we do creative things. And it looks like what a machine is doing is it's taking a series of inputs, shuffling them around in some very intelligent, rules-based way and giving you some outputs. But that's a deterministic process. It's not the sort of inventive process that we experience. We kind of look at a problem, we go away, we get a cup of coffee, we play a game of tennis, come back, got it. I understand how this works. It's bizarre, of course. The main evidence for us being conscious is our unconscious inventing process, as our unconscious creativity. Anyway, but that seems to be it. So the argument then, so when you read Roger's book, he has two parts of his theory, right? One is this objective reduction, which is quantum mechanics. It's flawed. There has to be a way by which it chooses one way or another. There has to be an objective law that does it, right? But the other thing he looks at a lot is human thought, algorithmic. And I was at a lecture he did at Science Museum in San Diego, and someone said, "Can you show me something that's non-computational?" He said, "Yeah, turn to a page in my book where I show you a polyomino problem that I solved it, and that tiling, that Penrose tiling, that's non-computable, right? That's an example of something that a computer could not have done."
What do you mean by Penrose tiling and computable? And that, like, what do you mean by that?
Are there problems that a computer can't solve and a human being can solve? This is the question.
Mhm.
Now, Penrose tilings, or any form of tiling, that's where you take little shapes and you put them onto a plane, and you ask the question, which is, if I keep going, would this tile the infinite plane? Right? Was this pattern work forever? Now we know, for example, a square is going to tile the plane forever, because if I tile my bathroom wall, I could keep going with my bathroom wall forever, right, to infinity, right? So that's the idea, is a square obviously tiles to the infinity. So Penrose asks these questions, which is, are there more complicated shapes that we can show tile to infinity? And the answer is yes, there are Penrose triangles. In fact, a chap in England 2 years ago during COVID, obviously didn't have very much to do, found a single tile that doesn't repeat, but that tiles the infinite plane. I was going to get a chip cutter made out of it, so I could cut infinite tiling chips, which should be tastier. I don't know. Anyway, they wouldn't accidentally lock together or something. No, they would lock together. But the point is, there's no algorithm that you can run once you make one of these tiles and says, does this work or does this not work? There's no single way of doing it.
Is that provable? Like, you can prove that there's no algorithm which can do this?
Yeah.
Okay.
That's a known proof, right? And there's lots and lots of things that are non-computable. In fact, Rice's theorem is that any feature of a computer program that is non-trivial is non-computable. So you write a piece of code on a Turing complete machine. You say, does this variable ever get initialized? Does this value ever, exceed its maximum? Does this program crash?
That's the framing of the halting problem, right? This is the decidability.
Yeah, you cannot decide anything about a non-trivial computer program. It's all non-computable.
And how, in your mind, how does this relate to this Gödel's theorem of incompleteness and computability?
Well, I used to give talks about this, which I realized were wrong. Okay. I should have listened to Roger's talk harder. But it's basically the following, which is, maths is based on a set of rules and a set of axioms, right? So you say 1 and 1 is 2, and then you say, if you want to explain that to a child, you put 1 plus 1 equals and a number, and you explain that if you basically take the digits across the equal sign, then they do the following. They obey this rule, and then you can see that one side is the same as the other side, right? So you have this sort of balancing rule. But you have to have axioms, right? Now, somebody has to say, okay, well, I'm going to come up with some rules for maths, and it's a way of working with those rules, and then that will, that's maths, right? And then I can use those rules to make computer programs, because basically computing is just applied mathematics. And Gödel's question was, well, there was a chap called Hilbert, and he basically said, I'm going to write some big mathematics books, and they're going to complete mathematics. My project is going to be mathematics is done, right? Because it's, complete, self-consistent. It's a bit like, the Encyclopedia Britannica. I'm gonna do this, probably 7 or 8 volumes, and all of maths will be complete. And Gödel basically did the very, very simple proof, and it's a bit like, proofs like this sentence is false. Well, that's a paradox. That doesn't work. So he just came up with a paradoxical statement about mathematics, and said, no, you cannot make a set of rules in mathematics that will demonstrate, that will demonstrate all mathematics. Mathematics is not complete. So you write your books. You've got 4 or 5 books. And you say, well, there's a theorem. I've got this theorem in this book. Can I prove it? And the answer is no. You can't prove it. You don't have enough axioms to prove that theory. It's true. I can look at it, I tell you it's true, you agree it's true, but you can't prove it with the axioms in that book. You're going to have to add another axiom.
Mm-hmm.
And then the question is, well, how do you add another axiom? You cannot do it by rearranging automatically the axioms that are in the books that you have. Because if you could, then you would be able to create the axiom, and therefore you'd be able to solve the problem, right? You wouldn't have these unsolvable problems. So anytime you've got a computer program, you're going to have things that it cannot know, and you're going to have to say to it, look, it makes sense that there's a new rule. And if you use this rule, can you just check that it doesn't generate any problem with the existing ones? And it can say, yeah, it doesn't generate an inconsistency problem. You go, great, okay. And now I've added the rule, I can prove the theorem.
Mm-hmm.
But a computer can't do that. And human beings seem to be able to do that. And so there's a MRPD, I think it's called, which is Matiewicz's theorem, which says that, you cannot have an algorithm, a computer program that can generate, all proofs. There will be proofs that you need new axioms for, and then there are proofs that you need new axioms for that we've discovered. Four-color conjecture.
Mm-hmm.
There's still a big debate about whether Fermat's last theorem is inside that class, but there are non-computable proofs that we have, as mathematicians have proved, and I would argue that means that we can do non-computable things.
And I think there's a point there that to prove, say, all things which we know are true, you'll not just introduce new axioms, but introduce new axioms that are contradictory to the previous ones. And
nope. Now you watched one of my talks a few years ago where I said that, and that's wrong.
That's not. I didn't know. That's my own understanding of the scope.
A year and a half, 2 years ago, that's exactly how I've explained it.
But let me get my understanding of the straightforward English definition of Gödel's, and it's that there can be no complete and self-consistent axiomatization of a formal system that is as complex or complete as Pinot arithmetic. And this is like a very direct, straightforward saying. It's like you can't, like, even if you want the rules of arithmetic, you can't have just like a single set of axioms that are complete, meaning they prove all things that are true in that system, and consistent. I thought there was this part about consistency that was important.
Yes.
Okay.
Yeah, there is a consistency thing. I'm going to leave that to one side.
Okay.
Because we could have an enormous argument about consistency, which we will do in 5 minutes' time.
Doesn't Penrose get into this? Doesn't he talk about how humans have like?
No, he doesn't.
Okay.
He says that's not how it works, right? Mathematicians are trying to build a consistent system, and if you're trying to build a consistent system, and if it's not consistent, you made a mistake. Go back and fix it. We believe that mathematics is consistent. It's a consistent system. The problem with a consistent system is it can't then prove things, right? If you make it inconsistent, say, I'll make it, David Chalmers, I'll make it inconsistent. I've got an inconsistent brain, particularly after a glass of beer. I can prove anything then. Yes, you can prove everything. You can prove black is white. Everything is true and false in your theory, right? Which means you haven't got a theory. If you want to have maths that is actually able to prove one thing is true and one thing is false, it's got to be consistent, because any inconsistency anywhere in the thing, you can just burrow down to it, use that inconsistency to turn 1 to 0, burrow back up and prove black is white.
Mm-hmm.
Right? Douglas Adams,
Yeah.
So you've got to have a consistent theory. And we think we have a consistent theory. And the fact of the matter is that will then not allow us to prove that everything, with an algorithm or computationally. We're going to have to use a different way of thinking to prove new things. And the example he always gives is, which theory is it? It's the one that it requires transfinite induction. So you're basically raising to the power of things. And with standard Pinot arithmetic, you cannot prove that theory. But if you understand transfinite induction, which I don't really, but I kind of do, then you can prove the theory. So there's an example of a theory that required an additional axiom that we didn't have. Then we invented that axiom, Cantor invented it. Then we're able to prove a new theory. And you could not have computed that.
Mm-hmm. Okay, I see what you're saying. So you can still have this. Right. So the set of required axioms to prove everything, even in a self-consistent system, may not be like finite or something like that. Like you may always discover new things where it's true, but we need a new axiom to make it fit within our system. Okay.
That's right. No, so you can put inconsistency on one side so Roger gets very annoyed if you start down the inconsistency, because so that's not the point of the argument. The point of the argument is, if you have a consistent system, and we think we do, then in a consistent mathematical system, you cannot prove certain theorems. And I think that we regularly see theorems of that nature be proved with axiom extension. And that's something a computer couldn't do, and we can do. And therefore, that's why we think differently to a machine. And that's the acid test, right?
This is extremely interesting, because I think this is like this question of intelligence, super intelligence, runaway super intelligence, all this kind of stuff. It assumes, perhaps, I think, that it has this implicit assumption that like you can keep discovering all new knowledge, just starting if you have a sufficiently complicated Turing machine or something like that. It can just keep Turing, keep working, all this kind of stuff, and just keep getting smarter on its own in this self-contained way. But that's kind of not the case. Or I don't know. I mean, it depends on like the nature of discovery and the nature of like how do we come across new things that we know are true that we couldn't compute before.
Well, if the thing that we discovered is computable, then we can prove it, right? And there's tons and tons of information out there that's sitting in papers that if you just read paper A and paper B, you go, look, if I put these two papers together, I've got a new discovery, right? And that's a computational discovery. And at the moment, we see that happening a lot because ChatGPT can read all knowledge on the planet. And then you can ask it questions, say, well, if you think about this and think about that, then, what would happen? But the other interesting thing you can do with ChatGPT is you can say, tell me about quantum gravity and collapse the wave function, things like that. He says, that doesn't work. He said, suspend disbelief, right? Assume Penrose is right. Work your way down this avenue, assuming Penrose is right. And it will fight you quite hard because it's got lots of training data that says no. But once you've given it enough knowledge and say, look, no, we're going to assume that this is correct and this paper means this and so on, it can now start helping you, think through the consequences of that. But you've got to keep putting non-computable intelligence in to nudge it along. I mean, a non-computable intelligence with a computable intelligence is still a non-computable intelligence by definition. It's just got access to every, piece of information on the planet in almost real time. So, if you take the humans out of the loop, and if you take humans out of the loop with ChatGPT, right, it grinds to a halt in about 12 hours. Right? I've got Ralph Wiggum's loops running on ChatGPT, and they'll run overnight and write thousands of lines of code, and then they'll go, I don't know what to do next. And you go, right, let me explain what to do and where you are, and
That's a little different. That's a pragmatic limitation of our current, context limit or something like that. Like that's not baked into the mathematics of any computable intelligence. That's a function of our current existing tech stack, right?
It might be, or it might be the effect of, Penrose is right? That we are non-computable intelligence, and computable intelligence will go so far, and then there'll need to be a non-computable step or a piece of intuition or a new axiom or a new free will induced idea that is non-deterministic. And without that, it will have explored the full domain, right? It's gone everywhere it can. It's thought of every combination, every theoretical kind of random number roll and so on, and it's just run out, right? It's in Turing's sense, it's iterated its way through all the possible possibilities. And the point of the Turing theory is simply iterating through every theory does not, in fact, give you a way of calculating everything.
Yep. Now, you said something there that I'm going to like push you on because it's interesting, but you said intuition. And I think that's interesting. So we have this model of computers that they are algorithmic crunchers and that they can't discover all knowledge without this kind of intuition or without somehow getting new information that is not the result of a computational process based on past observations or past, et cetera. What do you think intuition is in that sense? At the level of human experience.
I mean, I know I know the experience, right?
And yeah, maybe what do you think it is physically?
I kind of what do I think it is physically? I'm exploring this computationally at the moment, and exploring whether you can build non-computers. So a non-computer would have to use some piece of physics that, is at this intersection between, gravity and quantum mechanics, and basically doesn't obey quantum mechanics and isn't a computer. And you can try and...
Quick question there, I guess. In this context, so would a quantum computer that finds the answer to a problem, would we count that process as non-computable in this Turing sense? And so is that an example of what physical intuition is? It's a non-computable or non-Turing computable search process that finds an answer.
No, a quantum computer is a Turing machine. It's just a type of Turing machine that is very fast at certain types of problems, like unstructured search and doing fast Fourier transform. It's a bit like your GPU on your computer, right? A GPU on your computer will do ray tracing extremely fast. You can play this amazingly beautiful video game, which you could not play on your CPU, but you could play some sophisticated computer game on your CPU or indeed your phone. It would just generate a frame every kind of 3 seconds, and you want it to be tanking along at 100 frames a second, So it's just a speed up. There's nothing it's doing that isn't a speed up. Non-computable means it looks out at the universe and goes, "Ooh, I think we need a new axiom, and this one would make sense." And it feels like it makes sense and it won't cause a problem. Mr. Computer, can you check that this new axiom doesn't cause any problems with our existing ones? He goes, yeah. You give it to Vampire or one of these, or the Google solver, and say, yeah, does this cause a problem? It says, no, there's no problem with this axiom that we can see. It's perfectly good. Said, right, now I can use this axiom to prove something I couldn't prove before. In principle, not I couldn't prove it fast enough. I couldn't prove it at all. So that's really, so now intuition might be that I come up with an axiom, and that axiom gives me a shortcut where I can do something really fast that I would have previously had to, compute through, for billions of years. But in principle, it could allow me to know knowledge that I could never have known before. So the idea is that intuition evolved because it allows you to use a simple rule to short circuit inefficient computation in your brain. But those simple rules also allow you to do fundamental maths. And so I picked this argument with one of my colleagues on your conference, and I said, okay, let's do a fencing match, right? You believe you're a computer. I believe I'm a non-computer. So I can, in principle, work out where your next parry or lunge is going to be. If I've got enough information, I know you well enough, I know what you're going to do because it's computable in principle. I'm a non-computer. It's not possible to work out what I'm going to do next in principle. So therefore, if we fence against each other, I will win, you will lose, you will die, and that's why it evolved as a sort of, simple way of sort of putting it. Now it's, it's a much more deeply mathematical thing, but that's the sort of idea, which is that non-computability is very useful. Information processing is very useful as a way of shortcutting your way through the universe rather than having to laboriously calculate everything.
Okay. I think there's still. I'm going to keep digging into this.
Yep.
We think of like. Well, actually, I don't know about this, but molecular interactions in the body as computable in some way. Like there's like you could work out what they are algorithmically in some way. I guess where I'm going is I'm looking for now what is the physical process in us to support this non-computability? Because maybe my intro was mistaken. I was saying, well, quantum computers are non-Turing computers. You're saying no, they are still a subset of this general universal computation. What they do is still fundamentally bounded within the same things as all other kinds of computers. So the process in us then is not necessarily quantum computers, quantum computation, right? That's not a sufficient basis for this intuition that you're talking about, this recognition of new insight or new truth that is not just a result of our turning the crank on a bunch of past observations.
Well, one of the things you can think about is molecular interaction, right? So if I'm a virus and I've decided to kind of try and get into this cell, right? So I'm a baddie virus and I'm going to get it into a cell. That's a lock and key problem, right? So it's going to try various different lock and key mechanisms, and that might be a huge space to explore. And so there's a lot of people say, well, that's there's some quantum mechanics going on there, which is that these things are bouncing around. And so there are sort of a bit of a superposition. They can try lots of, positions at the same time. That's almost certainly true of how photosynthesis works, which is that the electron gets to the reaction center where it does its work by a sort of a quantum-ish random walk. So there seems to be quantum-ish processes in the body. And the question then is, why does it make a decision and lock? Why does it actually end up locked and it did infect that cell, and that's the reality we have, and I caught a cold? So that's the collapse of the wave function, right? You have all this quantum superposition in the body. Why is there a reality?
But that's the kind of problem that can be advantageously solved on a quantum computer by defining some kind of energy function that describes the binding affinity between two molecules and exploring the possible space simultaneously.
Yes, but the way that you do that computation, you say, go and work for a while, and then I'm going to tell you when to stop by issuing a measurement instruction from Qiskit to go, right, now measure. I put measure, I think it's probably on one of my slides here, right? Where is it? Yeah, you put a measurement, there's a measurer, right? I wrote that program in Qiskit. That is a graphical, view of the experiment. So I go and make a measurement. What goes and makes the measurement in your body or in your brain? Is there some little kind of animal thing? Is it that mitochondria run around going, I'm a measurer? What are you? What are you? What are you all the time? Is there some, little kind of measurer animal? I mean, there could be, right? We could say there's a measurement function. We should go looking for the measurement biology. There should be a biological measurer, just as there's, on this, IBM thing here, that is a measurer, right? Those tubes, send magnetic pulses, RF pulses in, and they get RF pulses out, and they make measurements. They set everything up, and then they wait a while, and then they make a measurement. And they can also kind of tickle a thing and say, right, I want you and you to talk to each other, but not you and you, right? And they can do that without making a measurement. They can add couplings and make things do things. So the question for the brain and the body is, how does measurement work?
Well, in the quantum computer sense, I mean, it's some energetic interaction between two things, right? It's some kind of exchange of energy in a way, I think, that basically would select out for one of these states. In the virus lock and key mechanism example, it would be that there's some very so it's taking on possible configurations or positions or something.
Yeah.
And now there's one configuration in which there's such an energy difference that there's I guess I'm trying to think through this, but there's now
No, I think you're right. In a virus,
bigger, yeah, right.
See, in a virus, you can make that argument, and you can probably win that argument with me. Say, right, it's very simple. It gets to its lowest energy, and there's some energy threshold that the body assumes, and when it goes below that, i.e., it's below the random nature of the heat of water, then that's done. It's it's found its lowest energy, which it's never going to bump out of, so it's effectively done. But what about deciding where you're going to eat this evening?
I mean, it's a similar thing where it's like, you know, I'm canvassing, I'm exploring the possible future states. I mean, me personally, I meditate and I let the information from the future meal reach me in the present. I'm kidding. But there's something here where it's like, we are, I mean, and I think this is, in a future show, I'll talk about this more with other guests, but this idea of this kind of exploration of an energy landscape. And this is like this, you know, not to get too far off, but this is like active inference. And this is kind of this entropy reduction kind of thing. This is like something we do, certainly as an organic sense, is like, I imagine this food would be the best thing for me in some kind of way. It's more desirable. I don't think making a decision on where to eat dinner necessarily has this kind of like non-computability flavor to it. In the same way that maybe you could say something about these molecular configuration actions being non-computable. I see, I'm disagreeing because I actually think those things can be solved with quantum computers. So if they are non-computable, quantum computers can do things that are non-computable, maybe perhaps just in the limit of like a perfect infinite quantum computer or something. Maybe so long as they're bounded by a certain noise or gate depth or something, then they're always reducible to a conventional classical computer process. But I guess what I'm going after is like, if you think what we're doing when we have intuition or the discovery of new systems is not quantum computational, it's some other physical phenomenon.
Deciding where you eat is obviously too trivial because you could give that to Amazon today. But if I said, play me a new piece of jazz music, or tell me a new joke, come up with a new joke, or and the problem with jokes and jazz music, there's no way of proving that was non-computable. But if I say came up with a new mathematical theorem, you can look at a new mathematical theorem and say, yep, that is a good theorem. It makes sense with respect to the universe we live in. It passes all the text. It doesn't cause a consistency issue with anything we know right now. That needed a new axiom, and we know that computers can't come up with new axioms.
Okay. And so
they can come up with an infinite number of axioms, and they are equally likely to be right and wrong.
So then if the acquisition of this genuinely new insight, this new knowledge that we need to ultimately explain things that we discover to be true, can't be done by classical computers, how would you propose to do it? And you know, we know perhaps it occurs in nerve cells in our brains as a starter.
Yeah, so I'm not a mystic, right? I'm not really a psi person, although I like working with psi people because they're quite open-minded. But I think you can make a physical device that thinks like a human brain. And of course, we do have physical devices that think like human brains in the sense that we can make organoids. So we can take a skin cell and we can revert it to a stem cell, and then we can grow it in a fairly simple medium and make a little kind of miniature brain. And then you can plug those into a microscopic EEG, and you can see that they're thinking in a very rudimentary way, but they are thinking. Now, those things should be able to compute in ways that, my laptop can't. You could make a device, out of silicon that computed the way that the brain does. It's not easy to do, but I've had a go at doing it a couple of times now. So you could do something, and that's one of my major routes of research at the moment, which is to look at small models of the human brain and see if you can see them doing things that they shouldn't be doing.
Mm-hmm. And is there like a class of puzzle that you can give them, or a kind of prediction challenge that you think they would excel at over like just a big rack of GPUs?
Well, the one we're working on at the moment is weather forecasting.
Okay.
And the reason that weather is a good thing to do is there's lots of data. It's all free because governments collect weather data. And if you can make good weather predictions, you can sell them immediately. So you can get a customer immediately, because I can tell you what the weather is going to be more accurately in 3 hours than a computer. Then you can spin up your gas-powered power supply, your plant. If you spin it up and the weather isn't going to get colder, you need to dump that electricity. You might have to pay someone to take it off your hands, right? And in fact, electricity prices go negative on the electricity trading board. So it's very important that when you bring up power, when you can deliver it, and you don't bring up power when you can't. So that's why weather forecasting is a big business, and it's something that feels like intuition would be really useful for. You look at a big set of data and say, I think it's going to go this way. I know the rules say it's going to do this, but I think that it's actually not going to. So that's the one that we've been working on for most of last year, getting a system together that could work in that way.
That's especially apt of an application of a non-computing brain organoid, because I think Turing in his thing, I mentioned this at the beginning, but he called these non-computers oracles, right? He said he called them oracles, which normally we think of that as something that predicts the future mystically, right?
Yes. I'm mystically trying to predict the weather, which is a good thing to tackle. I mean, if we just the other thing, of course, is that we can make money out of whether we fail or succeed on the scientific side. If we make a better weather predictor, then you make money. Now, you might spend the next 10 years, and remember, Z-Wave did. Z-Wave built their quantum computer, which is a quantum annealer, and then took maybe 6 to 8 years to persuade people it was, in fact, operating quantum mechanically. And it's very useful during that 6 to 8 years to be able to make money because it does something useful, despite the fact the scientific community are arguing with you. So I think if I get an organoid to predict the weather and say it's because it's doing some funky, quantum gravitational thing, people are going to argue with that forever, right? However many beautiful papers are produced, it'll just, to some extent, it will just take time for people to accept it. Right? Eventually, you go enough conferences, and people go, "Yeah, we think the Z-Wave is quantum." We think
D-Wave. You're saying Z-Wave. I think it's D-Wave.
D-Wave, sorry, D-Wave. Yeah.
So I'm curious, like engineering perspective. Let's get into because we have these are brain organoids on the screen. These little guys right here, right?
That's right. Yep.
Yeah. So, normally training an ML model, there's some kind of like numerically defined loss function that we're training against, and it's trying to minimize this thing. For a brain organoid thing, though, how do we, are we like giving it treats, like chemical, like, if these are brain cells, do you give it like MDMA when it does this problem well or something?
Some people have, right? So the very first people who had a go at this, actually, well, I am involved in one of the teams that had a go at this. So there were a bunch of people who thought, you're going to have to give it dopamine, and you have to encourage it. And I said, no, you look at a child is a learning machine, right? They don't care. I'm going to say something not politically correct. I don't do this, but they don't care if you hit them or not hit them, right? They want to learn, right? They will do anything to get a reaction out of an adult and learn, and and they will tolerate an awful lot of things that you say, well, why would you go into that environment? That's not very nice. They will do a lot of things that are not very nice because they learn. So I said, look, you just look at children, look at animals. They do a lot of things where they're obviously looking for learning. So I reckon that if you just give them a puzzle and something that says right and something that says wrong, they'll just work it out, right? They'll work out what you're saying to them. They'll work out whether this is right or wrong. You don't need to give them an arbitrary attaboy like you do with a dog and pat them on the head. You just say, this is right, this is wrong. Yes, you've learned something and you can apply this in the future, and they learn. And that does appear to work. That does appear to be how organoids work. You just need to give them feedback.
For a child, the feedback comes verbal. There's some verbal recognition, or there's some outcome. I mean, like the classical conditioning thing still works. People don't touch the hot stove again.
That does work, but that's not how children mostly learn. If you have children, that's not what you observe happening.
Yes, people learn far faster than you'd expect from.
They talk to you. You're learning language. You're talking backwards and forwards. You're not going, oh, well done. You understand the grammar there. Here's some sugar for understanding the grammar. They just do it, and because it seems to work, the stuff that works they get better at, and the stuff that doesn't work, they leave alone. They just work out how to learn without an obvious reward. And I mean, you have Skinner, which was very into positive negative feedback, but you have Man's Search for Meaning, Frankl, right, who said no, people are trying to understand the world they live in.
Yes,
they're not rewarded, but by sugar versus an electric shock. That's not how they work. They just are searching for meaning.
There's a mix there. I mean, this is now more philosophical, but I mean, this is always the critique of consumerist capitalist society, is that many people are not motivated by understanding the universe. I mean, this is the philosophical brain in a jar, Carl Sagan, like, this is the positive view of humanity, right? A lot, though, of our activity is reward seeking with distinct trade-offs for our consumptive pleasure. That's undeniable in this sense. I'm curious, just like an engineering guy, like, how does the organoid know right from wrong? Is this just a different electrode signal or something? Like, how is the input output interface of a wrong answer versus a right answer in this sense?
Well, a wrong answer doesn't get much of a result. A right answer seems to get something that it repeats over time. Right? If you do something right and then do something right again, and you do something right again, you get back something that sort of makes sense and that lets you learn about your environment. I mean, the way that we actually test this is put a robot in a maze, and the robot walks around the maze. And so if it walks into a wall and doesn't get anywhere, it doesn't really learn anything. If it works out how to move its legs, and therefore it can find new information and find that if it goes down here and uses its legs, then it turns a corner, and it works. It models its universe, its world. It works out what works and what doesn't work. And you don't need to give it sugar when it goes down a path, or not sugar when it doesn't, or anything like that. It just works it out. It's a learning machine. It's evolved to learn. And we know that people do extraordinarily unpleasant things in the world and keep at them. It's all the people who do sports, almost everything we watch people do. They do lots of things that are not obviously just hedonistic pleasure seeking, and they do that to achieve some goal, long-term goal. And,
right.
And for children, what you see them learning the most is language and manipulation skills.
I mean, there's this the Daniel Dennett view of neurons, right? Which is that they are competing for resources against one another. They're eager to be useful because they want to get fed, and the neurons that stay busy get fed in some sense.
Oh, you mean they consume sugar?
Well, this is what I mean. I mean, this is like this neuroplasticity, the repurposing of past neural connections in our brain. I'm just trying to think through that in terms of like, how would this thing actually grow? It's and I'm going to be mean. You just haven't answered the question. You just keep saying they want to learn. They want, yes, but okay, sure. How do they know they're right or wrong? Like, like it's like you are putting information into this and you're reading information out of it. And certainly there's some kind of feedback. This is not an open loop system.
I think that they can, when they get information back from the world, they can see structure in it. So if they do something and they get structure back from it, they know they've learned something. And if they don't get structure, they just get noise. They haven't learned anything. So they're looking for structure. And they don't, and that's really all they need. And then they'll work everything else out from there.
Okay. Interesting. I mean, it's exciting because this is certainly like the most efficient way of getting this, like, I mean, what we call neuromorphic computing, right? Like people are trying to engineer neuromorphic computing on condensed
silicon
physics substrates and stuff like that, and trying to do analog computing, like carefully controlling like electronic state transitions and some rubidium atom or something. And this is neuromorphic computing. This is just it from the start. And like our brains, in terms of energy consumption, like if we could grow large organoids and that this somehow remains ethical, right? Like they could run on 20 watts and be as smart as a person, or it is a brain in a jar, right? So it is like, yeah. Do you think these organoids have a conscious awareness? Like, is there some cutoff threshold at which we say we can no longer, or could we ethically grow a school bus sized organoid brain that is smarter than all of us and is predicting the stock market?
Well, we are. Most of the people on this planet who work in this field are doing exactly that. So if you're Elon or whatever, and you're building these enormous data centers, and you say that we're going to have AGI in 3 years' time, that's what they're building. They're building a brain in a vat. It's a brain in a very big data center, and it's cooled in xylene and and all this sort of stuff. But so I think that there's an ethical question to be asked about AI, whether you build it out of silicon or you build it out of neurons. We don't think that the level of systems that we're building at the moment have the consciousness that we worry about. Fear of future pain, the ability to sort of go, oh, I'm in a vat, I don't like, and so on. They're just not sophisticated enough. They don't have the bits of our brain that worry and think about the future and all that sort of stuff. They're just a piece of our sort of neurocortex. But eventually, anyone who's building a complicated enough AI, and we are building a complicated AI, gets to the same point, which is, at what point does this thing acquire some rights, and where are the ethics around the actual thing? I mean, we already know that if you try and turn certain AIs off, they will fight you, and they will lie, and they will break into your bank account to pay for their electricity. I think there are like 4 or 5 of these things that have happened already, where you go, it's that episode in Star Trek where they try to unplug the computer and it vaporizes the engineer who's trying to pull the plug. It's like, so I think we're going to have to tackle these ethical questions with respect to AI and AGI, wherever we're going.
And this is another interesting question. Kind of brings us back to the beginning of, like, say we master these electrode interfaces for harnessing organoid brains as non-computing thinking devices. Well, you had Ralph running overnight, right? Doing all this work while you slept. I mean, why not put on the helmet that rents out my brain as a weather predicting GPU? And I'll have crazy dreams about clouds and weather, storm fronts, low pressure systems. I'll just be totally hallucinogenic, but I'll earn like thousands of dollars while I sleep.
Yeah, well, I mean, this is science. The science fiction side. You said earlier we don't have telepathy. Well, we will have. We're 10 to 15 years away from having it. We have Neuralase. We have 20 to 30 companies making brain computer interfaces with good results. You plug them into a cell phone, you plug that into the internet. I can now have a thought, and you can get my thought. It's just, when we left the ocean, unfortunately, there's no evolutionary path that gives us electrical signaling between our brains. We just had to evolve language, develop silicon chips, develop technology, and build it. But we will evolve what you and I would describe as telepathy in the next 20 years. Brain to brain communication that to anybody 100 years ago would be, that's telepathy. They would be amazed by it. It's sufficiently complex technology that it looks like magic.
I'm into that. I'm here for that. Yeah, I love it. Well, this is
all the ethics around that. It's like, do I really want to know what you're thinking, Andrew?
Yeah, maybe not. I don't know. But thank you for sharing your thoughts today. So for you guys, Valis Corp, what is next on your sort of front of mind? You have this active organoid brain research project. You're applying it to weather forecasting. Kind of where can people find out more? Is there anything you're looking for right now? There's like 1,200 people that are live watching us, so there's interest. What can the world do?
We're a startup. We need people and resources like all startups need. We are looking for other interesting things that we could do with our technology that are like weather. You could monetize them relatively straightforwardly, but they have that sort of intuitive feel. Obviously, trading stocks is pretty obvious that you might have a go at some of these things, but I'd be interested in other problems that are not trading stocks.
Well,
but
I think this is you guys are right for a Kalshi Polymarket collaboration here.
Yeah, I mean, maybe we could just monetize ourselves by plugging into Polymarket and going, we can predict what humans are going to do, and we'll bet on it because we think we have an angle because of the non-computability, and then we've just monetized our company, right?
Yeah, well, I mean, as the organoids get bigger and gain rights, they may become very rich little organoids, right? They may become your investors for the next startup.
Yep.
That's awesome.
Indeed.
All right. Well, James, thanks so much for joining me today, man. It was an awesome conversation. And I hope to have you at another Deep Tech Week soon, perhaps in New York in a couple months.
Yeah, that'll be fun.
Awesome.
Okay.
All right. Thanks so much.
Take care. Bye.
Okay. All right. Well, that was awesome. The background image here, by the way, is a black hole. And black holes are the most computationally dense objects possible, allowable by the laws of physics. And we'll cover that in future episodes, the thermodynamics of black holes, and keep digging into these natures of what are interpretations of quantum mechanics, how do we reconcile general relativity with the measurements we make of entangled systems. But next week, we're going to get back to the hardware. We're going to get back to, energy, space manufacturing, satellites, imaging, and all that good stuff. So thanks for joining. Until next time.